Okay, so in this example, or in this video, I mean, we're going to talk about continuous compounding. And so what we're going to discuss is, well, what we've discussed up to this point is compounding where we give a value for n, where if it's annual or semi-annual or quarterly, weekly, monthly, those sorts of things. And we put in a value for n. So this time is, well, what if n gets bigger and bigger? Okay, how does that affect the amount of money I'm going to have, or how does that affect the future value or the amount of a? Well, that's what we're going to talk about today, and that's we're going to introduce continuous compounding and the idea of that. So, well, let's start with a thought process and say, okay, well, what if we suppose, what if we take $1 and we invest it at 100% interest? So in that case, our principal balance is going to be 1, so P will be 1, so that goes to 1. Our interest rate, since it's 100%, R would be equal to 1. So since R is equal to 1, we get 1 here. And so we simplified it to this expression here, so that it's only an expression in n. Okay? So now we can say, okay, well, what happens if n starts to increase without bound? What if n goes to infinity? Well, it turns out that as n approaches infinity, this expression 1 plus 1 over n to the nth power approaches this natural exponential e, or the natural base, e. And so this is a number that comes up quite often in the natural sciences and also in business. And so this is kind of neat because this introduced what we call continuous compounding. So what if we just let it compound where we don't use n, but we say it's just going to continuously compound? Well, now we're going to use this value for e, and e becomes the base of the exponential. And so that introduced this idea of continuous compounding. Okay, so we would say that if we have something that's compounded continuously, so in this case, if we have P dollars, so now let's bring it back to this. Well, what happens, okay, so we know this piece goes to E. Well, what happens to this, the general formula, as n goes to infinity? Well, now we're putting R and P back in. And it turns out that as you take n to infinity, keep P and R fixed, and P is deposited at an interest rate of R, and we're compounding continuously, which means we're taking n and we're going to infinity. Then we, for t years, then what happens is the amount of A, the accumulated amount, is represented by this formula here. A equals P times e to the RT exponent, or what I call PERT. So A equals P ERT, PERT. Okay, and so this is the formula that you use if it's continuous compounding. So be aware. If it's compounded where they give you n, you have to use the other formula, A equals P times the quantity 1 plus R divided by n, that quantity raised to the n times t exponent. Okay, so that is for compounding other than continuous compounding. If it's continuous compounding, we have to use this one. Okay, so keep that in mind. Okay, so next we'll do a couple examples.